Hello, do you have trouble doing simple bivariate analysis and when to use it? Do you have a problem analyzing an outcome that has a nominal variable? No problem. This video by the epidemiologist group will make you aware and skillful in doing such an analysis yourself. It will also give a beginner analyst an expert operational research skill with a multinomial outcome. The video is essential as a basis for analyzing a thesis or dissertation. The course is necessary for young researchers and those new to research who may have a problem manipulating statistics. It will also give the researcher a basis for multinomial logistic regression analysis. It is entitled Analysis Using Statistical Software, Multinomial Logistic Regression. It will enable young researchers to work and interpret the analysis of nominal variables as outcomes. It will also help the audience understand when to use multinomial logistic regression. We have learned the prerequisites for analyzing data, parts 01 and 02. We also discussed the analysis steps, starting with univariate, bivariate, and multivariable analysis, part 03. Furthermore, we also discussed the univariate analysis for categorical and quantitative analysis, which makes us familiar with our data. This session also discusses dealing with bivariate using logistic regression and cross-tabulation analysis. We will also use multinomial logistic regression to discuss a bivariate analysis having a multinomial or multichotomous outcome variable. The video will also have a practical analysis using SPSS for Windows. If this is your first video, please click the subscribe button. We also encourage you to view the whole video and click the like button if you like it. As in previous sessions, we discussed the 3 analysis steps in the third session, especially for operational research. The first step in the analysis is univariate, followed by bivariate analysis. As the name implies, bivariate analysis looks at a relationship between 2 variables. In operational research, each variable in the data is assessed against the outcome variable, one by one. The analysis results are crude findings because no adjustment is made for a third variable. For this model, we will go through the details of the analysis. The type of analysis differs by the type of variables, among which a categorical variable is an outcome. There are 3 possible forms of analysis when the outcome variable is categorical. The first is when the outcome variable is nominal and dichotomous, using binary logistic regression. The second form of analysis is when the outcome category is multinomial. That is, a variable has 3 or more options but is not ordered. It uses multinomial logistic regression. We will deal with this type of analysis in this video. The third form of analysis, when the categorical outcome variable is ordinal regression, which will be given in the future. The third and final step of the analysis is the multivariable analysis. Although we will discuss this in the future, the multivariable analysis is done to gain insight into causal relationships, i.e., cause and effect relationships. The bivariate analysis. It is the second step of the analysis and is the initial step in hypothesis testing. It is the analysis made between 2 variables to assess the presence of an association. It usually answers the question, is there an association between these 2 variables? Before we continue, be sure to subscribe to our channel and ring the bell to get notified of our latest video. What possible combination exists? As in the previous video, there are 3 possible combinations of variable types. These include a combination of first, when the 2 variables are qualitative, that is, when the predictor and the outcome variables are qualitative. The second is when one is a quantitative and the other a qualitative variable, especially when the outcome variable is quantitative. The third possible combination would be when both variables are quantitative or continuous. This session will deal with a combination of 2 qualitative variables. How to deal when both variables are qualitative. Here, we give more emphasis to the outcome variable. The 3 possible categorical outcome variables could be 1. When the outcome variable is dichotomous or binary. The second is when the outcome variable is multichotomous, multinomial, or has 3 or more options. The third is when the outcome is of the ordinary form, that is, when it has order between the possible options. It usually has 3 or more ordered options. The first is when the outcome is a dichotomous variable or a variable having only 2 options. This is a common outcome in public health and clinical medicine. Examples include death versus non-death, case versus no case, having HIV against not having HIV, etc. The analysis is usually cross-tabulation followed by binary logistic regression. The cross-tabulation would be for the description, whereas the binary logistic regression would be for further analysis. The second form of the outcome variable is the multinomial variable. It is usually considered when the outcome variable has 3 or more options. Examples of this category include getting any acute febrile illness, malaria, meningitis, or typhus. Group of disease patients at OPD. The analysis is usually a cross-tabulation followed by multinomial logistic regression. Cross-tabulation is for the description, as in the dichotomous form of analysis. In contrast, multinomial logistic regression is used for further analytic analysis. In this video, we will deal with this form of analysis. The second form of the outcome variable is the ordinal variable. When the outcome variable is of 3 or more options, the options are ordered. For example, here are the mild, moderate, or severe symptoms of depression. The analysis is usually a cross-tabulation followed by ordinal regression. Cross-tabulation is for the description, as in the dichotomous form of analysis, during the ordinal regression for further analytic analysis. What is a multinomial logistic regression? Multinomial logistic regression is often called multinomial regression. It is used to predict a nominal dependent variable for 1 or more independent variables. It is sometimes considered an extension of binomial logistic regression. It allows for the dependent variable to have more than 2 categories, but not ordered forms like in binary logistic regression. Like other types of regression, multinomial logistic regression can have nominal and/or continuous independent variables. It may include interactions between independent variables to predict the multichotomous outcome variable. What assumptions should we make? Assumption 1 follows that the dependent variable should be measured at the nominal level with 3 or more variable values. Nominal is when there is no order between the attributes of the variable, e.g., ethnicity, sex, marital status. The nominal could be dichotomous or multichotomous. However, here in this scenario, the outcome variable should be a multichotomy with 3 or more value attributes. The second assumption would be the need to have 1 or more independent variables. The independent variables could be continuous, ordinal, or nominal, including dichotomous variables. However, ordinal independent variables must be treated as either continuous or categorical. Before we continue, be sure to subscribe to our channel and ring the bell to get notified of our latest video. The third assumption is related to the dependency of variables included in the analysis. There should be independence of observation. The variables should not have any known relationships in data collection or assignment. Moreover, the dependent variable should have mutually exclusive and exhaustive categories. There should be 2 options for the outcome variables for a predictor, that is, no individual belonging to 2 different categories. The fourth assumption is related to multicollinearity. That is, during multivariable analysis, 2 or more independent variables have a strong association. In this scenario, there should be no multicollinearity. Multicollinearity occurs when you have 2 or more independent variables that are highly correlated with each other. When highly correlated, their prediction power will be cancelled by each other, which can lead to an unusual relationship. The fifth assumption is related to outliers and influential values. It usually occurs when the predictor variable is a continuous variable. There should be no outliers, high leverage values, or highly influential points for the continuous scale variables. What is an outlier? It is usually for a continuous variable. Outliers are extremely different values that could influence the whole regression. An outlier may be outlying in X space, Y space, or both. Depending on their location in space, outliers can have moderate to severe effects on the regression model. How should we specify the control value of the outcome? In logistic regression, the coding schemes of the outcome variable, the control, are coded as 0 and the treatment as 1. For multichotomies with categorical predictor variables, the recoding becomes a little bit different. We should specify well to choose the proper first or last as a control group. We should specify the first coded 0 as the control, 1 as the second group, 2 as the third group, and the fourth group as 3. What are the steps of analysis in multinomial logistic regression? First, the data is entered in a multivariate fashion. The reference category for the polychotomous categorical outcome is codified as 0. By clicking Analyze. Then drag the cursor over the regression drop-down menu. To choose and click on multinomial logistic. Furthermore, click on the multichotomous categorical outcome to highlight it and click on the arrow to move the variable into the dependent box. Continue by clicking on the reference category button. Click on the first category marker to select the control in the reference category. If it exists in the first row or the last, if it exists at the end, click Continue. Continue by clicking on the first categorical predictor variable to highlight it, and then click on the arrow to move the variable into the factors box. Repeat the above two steps until all variables are moved into the factor S box. This is for multivariable analysis. Moreover, for continuous variables too, click on the first continuous predictor variable to highlight it, and then click on the arrow to move the variable into the covariate S box. Repeat the steps until all continuous variables are moved into the covariate S box. Click OK. This is also for multivariable analysis. As a practical procedure, by clicking first, Analyze, dragging the cursor over the regression drop-down menu a second time, and choose and click on multinomial logistic as a third procedure. The multinomial logistic regression selects and clicks on the multichotomized categorical outcome to highlight it from the list of variables. Then click on the arrow to move the variable into the dependent box. Continue by clicking on the first categorical predictor variable to highlight it, and then click on the hand to move the variable into the factors box. You may repeat this selection and send it into the box until all of the categorical variables are moved into the factor S box. Moreover, for continuous variables, click on the continuous predictor variable to highlight it and click on the arrow to move the variable into the covariate S box. You may repeat this selection and send it into the box until all of the continuous variables are moved into the covariate S box. Continue by clicking on the reference category button to specify the reference category. Finally, click OK. Remember, only one predictor variable is selected as a bivariate analysis, and the result will be crude. A crude result is unadjusted for the influence of other variables. Usually, categorical predictor variables are moved to the factor S box and continuous variables to the covariate S box. Let us look at example data for demonstration. We want to see if the diagnosis of patients coming to the outpatient department OPD is predicted by the sex of an individual. The outcome variable is diagnosis of a patient, and the predictor sex is categorized. The diagnosis of a patient includes 0 for no case, free of a disease, 1 for infectious disease, 2 for non-communicable disease, and 3 for non-specific disease. The predictor of sex is categorized as 1 for females and 2 for females. We should put the nominal outcome variable into the dependent, then the categorical predictor variable into the factor box, or the continuous variable transfer into the covariate box. Finally, click on the reference category. Click on the first category marker to select the control in the reference category. If it exists in the first row or the last row, if it exists at the end, click Continue. If you do not specify it, the procedure will automatically choose the last category by default. It would be best to treat each outcome category in either ascending or descending order. It is optional, but the following is after clicking the statistics and choosing the checkboxes: cell probability, classification table, the goodness of fit, and monotonicity measures. It should resemble what follows. What steps should we follow to interpret the SPSS output? First, look in the model fitting information table under the significance column. This is the p-value that is interpreted. If it is less than 0.05, the model fits the data significantly better than the null model. Continue with interpreting the results. If it is more than 0.05, the model does not fit the data better than a model with no parameters. Let us look at the following output from SPSS. The case processing summary summarizes the variables. It shows the proportion of the outcome as well as the predictor variables. It also describes how many study subjects were included in the model. First, the model fitting information. Look in the model fitting information table under the significance column. This is the p-value that is interpreted. Since the p-value is less than 0.05, the model fits the data significantly better than the null model. It describes well whether the model is good enough at showing a relationship. So we may be ready to reject the null hypothesis. The second is interpreting the pseudo R-square. What is pseudo R2 in logistic regression? It is based on the likelihood, which is based on pseudo R-square comparisons between the likelihood of the estimated model and the likelihood of the null model. The null model contains no parameters, but the intercept pseudo R-square can then be interpreted as a measure of improvement over the null model in terms of likelihood, thus indicating goodness of fit. It is thought to measure the percentage of the variance. This is true for linear regression. However, for logistic regressions, we should interpret them with great caution. The three forms of pseudo R-squares are based on authors, although McFadden is more conservative. The third condition needing interpretation is looked at in the likelihood ratio tests table in the significance column. It is the p-value that is interpreted. If it is less than 0.05, that variable has a significant overall effect on the outcome. In contrast, if it is more than 0.05, that variable does not have a significant overall association with the outcome. The likelihood ratio tests table here is as follows. It is essential when it is for multivariable analysis. It shows how the predictor variable predicts the outcome variable. This table is primarily helpful for nominally independent variables. In this analysis, the p-value is below 0.001. Therefore, continue interpreting the results, so we should be ready to reject the null hypothesis. Before we continue, be sure to subscribe to our channel and ring the bell to get notified of our latest video. It is interpreting the parameter estimate for categorical predictors. For categorical or ordinal predictors, if the p-value is less than 0.05 and the odds ratio with its 95% psi is above 1.0, the likelihood of the outcome occurring increases many more times than the reference category outcome. Suppose the p-value is less than 0.05 and the odds ratio with its 95% psi is below 1.0. In that case, the likelihood of the outcome occurring many times decreases compared to the reference category outcome. In the example above, we may interpret the findings from the parameter estimate as follows. Based on the first raw on infectious disease was 1.57 times 57% more likely to occur among women than in men than those with no disease, odds ratio equal to 1.57, and a 95% confidence limit between 1.21 and 2.02. For the second raw, non-communicable diseases were 55% less likely to occur among women than in men, as compared to those with no disease, odds ratio equal to 0.45, 95% confidence limit between 0.32 and 0.63. Before we continue, be sure to subscribe to our channel and ring the bell to get notified of our latest video. For continuous predictors, if the p-value is less than 0.05 and the adjusted odds ratio with its 95% psi is above 1.0, for every 1 unit increase in the continuous variable, the risk of the outcome occurring increases that many more times versus the reference category outcome. If the p-value is less than 0.05 and the adjusted odds ratio with its 95% psi is below 1.0 for every 1 unit increase in the continuous variable, the risk of the outcome occurring decreases that many times versus the reference category outcome. The example took the outcome variable to diagnose patients coming to the outpatient department, OPD. The outcome variable diagnosis of a patient is predicted by the age of the individual study subject, having a category of 0 for no case, free of a disease, 1 for infectious disease, 2 for non-communicable disease, and 3 for non-specific disease, and the predictor age is a continuous variable. Select the dependent nominal outcome variable and transfer it into the dependent box. Move the continuous predictor variable into the covariates box. Then click the reference category to select the reference. Here, on this slide, the summary of the variables shows the proportion of the outcome, but not for the continuous predictor variable. It will also describe the number of missing values. In this case, it was none. This slide shows similar slides to the analysis when the predictors are categorical and the interpretation of the above outputs, like model fitting information, pseudo R-square, and likelihood ratio tests table, is similar to the categorical predictor variables. This slide shows the interpretation of the predicting estimate for continuous predictors as follows. Suppose the p-value is less than 0.05 and the adjusted odds ratio with its 95% psi is above 1.00 for every 1 unit increase in the continuous variable. In that case, the likelihood of the outcome occurring increases many more times than the reference category outcome. However, suppose the p-value is less than 0.05 and the adjusted odds ratio with its 95% psi is below 1.0 for every 1 unit increase in the continuous variable. In that case, the likelihood of the outcome occurring many times decreases compared to the reference category outcome. In our example above, the first raw for every 1 year increase in age, a person's probability of getting an infectious disease decreases by about 2% 1.00.98 compared to the control group, with an odds ratio of 0.98 and a 95% confidence limit between 0.97 and 0.99. For the second raw too, for every year increase in age, a person's probability of getting infectious disease increases by about 2% 1.018 1.00 compared to the control group. The odds ratio is 1.02, with a 95% confidence limit of 1.02 to 1.04. However, there is no association for the third raw due to the p-value 0.05. R equals 1.02, 95% psi, 1.00, 1.04. Notice that the 1.00 must be below 1, and it is an approximation that brings us to 1.00. Before we continue, be sure to subscribe to our channel and ring the bell to get notified of our latest video. Before we continue, be sure to subscribe to our channel and ring the bell to get notified of our latest video.